of static equilibrium to that system.
We're
I
live.
think okay, good. So if you go to slide 3, you see there I write out the conditions of static equilibrium on the right, and I quote Newton's first law as he actually wrote it in the Principia, and it's really worth doing that because Newton's laws have been kind of bastardized down into forms that are not as clear as he himself wrote them in the Principia. So when we get to Newton's second law, I'll make that point as well. So let's just read Newton's first law and really tear it apart a bit. He wrote every body, of course, he wrote this in Latin, so it's not exactly what he wrote. Every body perseveres in its state of being at rest or of moving uniformly straight forward, except insofar as it is compelled to change its state by the forces impressed. So that's a little flowery language for our brains these days. But let's see what that says. Every body, everything, every object continues in its state of being. Right? That state is really important. The state that he has in mind is what its position and velocity are. So in particular, what its velocity is, its state of being at rest or of moving uniformly straight forward. And he later makes it clear that, of course, being at rest just means relative to you, maybe, or some reference frame you've chosen. An object being at rest is an object that is moving uniformly straight forward to somebody else. So those two things really are the same thing, as we'll see when we talk about reference frames. So it continues in that state, really, which is of rest, except insofar as it's compelled to change, unless it is forced to change that state, change that velocity by forces that act on it. That's what it's really saying there. And so we're really taking that first law and we're just looking at the first part. A body that perseveres, continues to be in its state of being at rest or constant velocity because there is no net force on it compelling it to change. The equations of static equilibrium are written there at the right, and it says that the sum of all vector forces, that little sigma at front means add up all of the vector forces on an object, and you should get 0. Adding up vectors means kind of taking into account their directions and being sure that they all add up in every possible motion, x, y, and z if you want, to 0. So that's a vector equation. It really stands for 3 equations. It means there's no net horizontal force to the right or left. There's no net vertical force to up or down. There's no net horizontal force front or back, if you want to think of it that way. Just in general, because we live in what seems to be 3-dimensional space, there should be no net force in any one of those 3 directions. And the same thing is true for torques, turning forces. Things can turn around a vertical axis. They can turn around a left-right axis. They can turn around a back to forward axis. And they can turn around any combination of those. And if there's any turning force that will make something change its state of rotation, then that's what's called a torque. And we'll talk about torques in a very simple manner today. But those are in general 6 equations there. 3 for the 3 components of force and 3 for the 3 components of torque. And we'll get back to talking about that in the context of this particular problem. So we're going to look at this situation. It's a straight bar that is held in a horizontal orientation by 2 ropes. We've got, Ben is pointing at things for you, I think.
No, I'm not.
You,
I'm just kind of scanning over it, but
okay.
Yeah.
Somehow,
I don't think my
I'm
pointing is
seeing
helpful.
your pointer.
Yeah. Oh, really? I think it's only you.
It's my
Maybe
pointer.
Is it yours?
If you're seeing something over the screen, like now over
Well, it says Ben Tristram on it.
No, yeah, it's only you're seeing that, John. I was just kind of jump. So don't worry.
You
Oh,
are on
okay.
the
All
Google
right.
Doc. Sorry. If you're on the Google Doc, no, it's not me. I'm following you actually.
Okay, good. So I'm not. I guess I'm not. Sorry for the interruption. I thought maybe that was you at first. But that's all right, Ben. If you care to do that, that'll be fine. Oh,
But
I
since
guess
you
it
stopped,
doesn't matter. Nobody else is going to see it.
yeah.
Okay.
Since you stopped, let me just tell you something. So
Yeah. Hmm.
I will paste a link in chat a minute later from now, which will lead people to the Jitsi where we usually do the thing, and it's not the YouTube because there is a delay. So I will be able to draw. I will be able to point things either on the slides or on a blank sheet. This is the plan for today. But if you need this at any time, just let me know. Yeah, that's it.
Okay, good. Thanks, Shamash. Okay, so we're going to look at that situation. It's a beam, a straight bar is held, or a rod, I guess I should say, is held in a horizontal orientation by two ropes attached to its ends and to the ceiling as shown. And that's it. There's two ropes attached to that rod and it's held in that position. So before going on, I just want to stop for a moment and just ask you if your intuition tells you anything about what's going on. In particular, do you think it's even possible? Because I think if you look at this situation, you think about, I mean, suppose you just attached lines to a rod and then held them in your hands and kind of pulled them out. Do you think you could do this? Do you think it's possible? Does your intuition tell you anything that you might that's about this that's odd or um, uh, I don't know, anything? So if anybody would like to answer that question, I'm being purposefully vague, but I think it's always worth looking at a situation and trying to apply your intuition about what you think may be going on. Notice I haven't asked you anything about it. We're just going to apply the equations of static equilibrium to this situation and see what we can find out. And I'm going to, at the very end, I'm going to talk about that being the right way to work physics problems, even if this were a physics problem and the professor asked you to find the weight of the beam or something like that. You should approach it the same way. That is to find relevant physics and apply the physics and see what you can find out. But now I'm going to shut up if anybody wants to try to address the question I asked. I'll give you a few seconds here.
I did come up to speak about this, but I'm new to the stage, so I wanted to I don't
That's
want to speak
fine.
too much.
You're welcome. And did you want to say something about it?
Yes, hi everybody. Yo, John, I don't know what it is. Every time I have a serious question, I come on Clubhouse randomly, and then boom, you're like answering or you're talking about it, and I'm like, what is so cool? Okay, so okay, basically the description that you're describing, I have a understanding of it from a different perspective, right? From a different paradigm, but the science of it is what I am going to like ask to, like paralleling the words basically, because okay, so the way that you're describing it to me is, you know, the pendulum.
Mm-hmm.
Okay, so, and I'm coming from a perspective of like, there's universal truths, right? And one is that the one I'm holding is that our existence came into existence. Okay, our, like, you know, the singularity, all that stuff, it have happened, right? Which means that like all the energy that's in our reality, it cannot be created, it cannot be destroyed. So then, where did it come from? It had to have been inputted at a specific measured amount. This is my paradigm, okay? And the measured amount is from an outside source. Now, the
So
part you're
can I just stop you for a moment here? I don't know if this is a preamble to to answering my question about intuition
yes,
on the situation.
yeah.
That's fine. Otherwise, it sounds like something maybe I'd be happy to talk more
No, it is. It
where
is.
you're
I'm giving
going
you
in the
the. I'm giving you
discussion.
like the premise of where I'm coming from, like the pendulum.
Okay.
What the pendulum would look like, because so what you're describing to me is a pendulum, right? But then
Well,
taking that
so
past.
actually, let me
Go ahead.
let me say this about that, because when you said pendulum, I thought I should. It's a good thing to think about. For instance, in this case, I think it should be, hopefully, if you understand the situation, it should be pretty clear that I could reach out and push that beam a little bit to the left, let's say. And I hope your intuition makes it
Yes.
pretty clear that if I did that, it would rotate a little bit counterclockwise as it moved to the left. It would be forced to rotate because of the constraints provided by the rope. Does that make
Yeah, absolutely.
sense?
This,
Right.
this, this is why I'm saying.
And then it would rock back and forth, right? Like a
Exactly.
pendulum.
This is
Yeah.
why I'm
Okay,
saying.
go ahead.
So this is why I'm using the pendulum as an example, because it is a closed system. This is how I view our reality. Our existence is a closed system, but within its system itself, all the energy is like it's entropy. You know what I mean? So when you have an individual or people or whatever who recognize that they can be static in that system, or they can be the change maker. They can be the one that goes left or right. And first, it's you are being pushed once it got started, and then it becomes an equilibrium gets hit. Then now you have like you have agency basically. So then this is the outside the box part, okay? Which is when you recognize that you can be static, actually literally, I'm talking like wave particle duality like that, you can actually achieve this, then you have disorder. You can get into actual chaos because now you have entropy with no limit.
Okay, so I am going to. I appreciate your contribution, but I do want to keep this very much. This is really is a course in physics,
Okay,
and we can talk about. I
I'll
think
go
where you're
down.
getting
I'll go
into
down.
is kind of
I'll go down.
sorry.
I'll go down to audience, but I just wanted to ask about this one part and then I'll go down because
Okay, go ahead.
to go back to the pendulum part. Okay, if so, okay, the pendulum's swinging and then now it stopped. Now you have you or whatever it is or the body in the middle, right? And you can push it left and you can push it right. My question is there a way to determine through physics which direction? That's
Which
the question.
direction to push it?
Yes, if you are static, can you determine a direction?
Yeah, well, okay, so I think you're getting kind of at this. I think this is a good point. Um, I am telling you, and you need because it's part of the problem statement that this thing will be in equilibrium. This thing will be horizontal like this, and part of the kind of unspoken what I haven't told you, but which should be understood from that is that if I do push it just a little bit to the right and let it go, or I'm thinking to the left, it doesn't matter. But if I push it a little bit to the left, clearly those strings will have to adjust. They will make it turn a little bit counterclockwise as I'm doing that. And when I let it go, it will now move back to the right. I think your intuition, to the right, yeah. I think your intuition should probably tell you that. And it will be swinging like a pendulum, as you said. So it will overshoot the position that I'm showing in the picture, and then it will move a little bit to the left. Sorry, to the right, and in so doing, it will be forced by the strings to rotate in a clockwise direction until it finally clearly it can't move too far to the right or left because it's got those strings attached to the end. So even as far as it could possibly move, it's going to come back. And the fact that I'm telling you that this is the position that it will stay in really kind of means that it wouldn't stay in any other position, that if you released it in any other position, it would oscillate. So I hope your intuition kind of makes that clear. At the same time, that your intuition may be screaming you that there's something weird about this. And I was hoping maybe to get somebody to at least tell me what it is that's a little weird about it being in equilibrium. You know, do you think it's possible that a rod could be? Don't you think my intuition? Here's what my intuition tells me. My intuition tells me, looking at this, I think this thing ought to want to move to the left a little. And I can tell you why my intuition tells me that. Andy, did you want to say something?
Well, yeah, I was going to say the same thing. It doesn't look like it's stable to me. I mean, it might be, but just because you draw it, and I mean, perhaps you chose those angles and tensions carefully, whatever. But it, it looks to me like if you started in this position and you released it, it would want to go to the left and get all like. There's no reason why it needs to be horizontal, right? But I don't know, maybe this arrangement was chosen carefully and it is in fact an equilibrium. It doesn't look like it is to me.
I have
That's
an
exactly
answer.
the response I wanted. Go ahead, Mo.
Yes, but I'm, let's say, perverted on this subject. I would take vectors, and I know there are at least three vectors. One vector for each rope and one vector for the force of gravity. So the force of gravity, let's say it's a vector of length 1 in any specific unit, but just 1. And the other two should cancel each other. So there should be like symmetric vectors, but of the same length. I don't know if this is what you
Yeah,
expected as an answer.
and we're gonna do exactly the kind of thing you're hinting at there, Mao. So absolutely. I mean, if you look ahead, you'll see this is exactly the kind of thing we're going to be doing. So that's a great comment too. But Andy's comment, Hero's comment, I know I should call you Hero, Andy, because that's what everybody else sees you as. So I will try to do that. That's exactly what I was looking for, because I wanted you to kind of if you think about this, I think most of you would agree that just because of the angles of those strings, they can't. It seems like it ought to move over to the left, but I'm telling you that it doesn't. And your intuition might even scream out and say, I think you're telling me something that can't be true. I'll show you that it can be true. But it's
And I
good
think you're saying
to,
it doesn't with this particular set of angles of strings, right?
right, that somehow, if I could always take strings and hold them in such a way that the bar would be horizontal. But I'm telling you, and notice that it doesn't really matter. I hope it's clear. Maybe it isn't. I hope it's clear that it doesn't really matter that those strings are both attached to a horizontal ceiling. If I just detached either of those strings and held it in my hand, so that it was still in the same direction. The only thing that really matters is the fact that one string is pulling much more horizontally on the bar than the other string is. And that's the weird part.
John,
Okay?
um,
Yeah, go
I
ahead.
have a trick to use intuition, and it's when you see a diagram, you try to change one of the condition in an extreme way, like having a rope that is really, really long, or string, or really, really short, and try to imagine what would happen. Uh, so that might give you an idea. And I use that in mathematics, for example, for demonstration. So probably that's one way of
Yeah.
exploring at first the problem.
Well, so for instance, I mean, one thing you could do, imagine that I took that string on the left and I kept it attached where it's attached to the ceiling and the bar, but I just made it a longer rope. I just made it a longer rope and nothing else. I didn't change the attachment points. I just made it a longer rope. Then obviously it couldn't be held in this position, because in this position that rope has to be the length that I'm showing there. If I attached a longer rope, it would have to find a new equilibrium. So two things should be clear. The equilibrium that it finds depends on the attachment points. And number two, there will be an equilibrium. There will be an equilibrium position. There will be a place where I could hold that bar and move it around by hand until I found the place where releasing it just keeps it right there, right? I could just physically do that. So we're spending a lot of time talking about our intuitions about this, and I think maybe we've done enough of that. But I think it's really important to do that. Use your intuition; it helps guide you and things that you might be looking for as you move further. let's move further. Let's go on to slide 4. So the way we actually approach a problem like this is by drawing what are called free body diagrams. And the first step in drawing a free body diagram is to be very clear about what the system is that you're claiming is in equilibrium, the system to which you will apply the condition of equilibrium. Sum of forces equals 0, sum of torques equals 0. And in this case, it's the bar itself, right? It's not the bar and the ropes. It could be. I mean, I could do that too. But I propose to just look at the bar. And I literally, when I teach this stuff, I tell students, I want you really to draw the picture and literally to take your pencil and draw a dotted line around the system. This is important. You can't do it in your head. You have to literally, at least at first, until you get good at this, draw this dotted line, because what the dotted line allows you to do is then to go around very carefully and look for things that touch the system. Because unless something touches the system, there is no force being applied to the system, with one and only one exception in this series. Later on in physics, we'll find other exceptions. But the only exception that's ever going to apply in this whole series is a weird force that we call gravity. It's a force that acts on something without any need for touching it. And that should strike you as weird, and it should also convince you that using this method, you need to identify all the forces that act. And the way you do that is by being very clear about things that are touching. There are only 2 things touching this system. And so there are only 2 forces plus that weird force that acts without needing to touch. So we're really clear now that there are 3 forces acting on this system. And 2 of those forces in this particular case happen to be forces that are exerted by strings, ropes, springs. When you have things like that, linear things touching a system, those things exert what we call tension forces. And we can talk about the tension in a rope. The idea there is that when we talk about the tension in a rope, we are really talking about the force that any part of the rope exerts on the part that's right next to it. So if I imagine taking a rope and cutting it, I now, of course, the rope will come apart. But if I wanted to hold it in place, I would have to exert a force equal to the tension in the rope on the part on the left and a force equal to the tension in the part on the right in order to keep them there. Each part of the rope exerts the equal and opposite forces on the part next to it. And that force is the tension. This is kind of getting into what's called Newton's third law at some point, but the tension in a rope is the force that one part of the rope exerts on its neighbor, and that neighbor exerts on it in the opposite direction. And at the end of a rope, it's the force that rope exerts on whatever's attached to it. So when you know the tension in a rope, that tells you all sorts of things. The force that every part of the rope exerts on every other part of the rope, and the force that the rope exerts on whatever it's attached to. So in this case, the tension in the rope is the force being applied to the rod. And then the only other physics adage you need is you can't push a rope, because you can't push a rope. Ropes exert forces that are always directed away from their point of attachment. So that string on the left, the rope on the left, is exerting a force on the left end of the beam that is up and to the left on that point, and the rope on the right is exerting a force on the beam that is up and to the right on the beam. So those are 2 of the forces. And then there's this gravitational force, which is downward. The gravitational force on an object is always downward. By definition, down is the direction of the gravitational force, and that and we give the amount of that force the name weight. So when you weigh yourself on a scale, you're getting the amount of the gravity. You are determining um, the force of gravity on you through a process that's actually itself bears a little examination, but I won't get into right now. Any comments on that? Sorry, I'm being probably overly pedantic. It probably sounds overly pedantic, but it's really important to be very clear about the process you're doing. So we've gone through this now, and we've discovered three forces, one of which is downward, one of which is up and to the left, and one of which is up and to the right. And having done that, we move on to slide 5 and really draw our free body diagram, which is to say we take those three forces and we move them without changing their direction. We transport those vectors, as it's called, so that they're all tail to tail. Each of those forces is now connected at its tail, so that I can really see the directions that they are, and the force that I called T1, the one that I actually gave you a value for, the magnitude of that force is 50 pounds, and it's directed 30 degrees above the horizontal to the left. The force T2 is directed 60 degrees above the horizontal, but I don't know what the magnitude of that force is. And the gravitational force, the weight W, is directly downward. And I put them tail to tail, and then I have to choose a coordinate system in order to find the components of these forces and get the two vector equations it turns out that we get in this particular case. I choose a clever coordinate system, and clever really means choose a coordinate system so that at least one of the forces is really easy to to suss out, to figure out what its components are. In this case, as in many cases, that clever coordinate system is just one with x being horizontal and y being vertical. But it's important to understand that I probably should have done this same analysis with x along the T1 direction, or I could have let x be along the T2 direction. And in fact, I don't even need the y coordinate to be perpendicular to the x. I just really need two different directions. But that's getting a little deeper than I want to right now. Let's just choose this clever coordinate system. And then, as I've done on this page, analyze the so-called components of these forces. And to help us with that, the reason I chose the 30-degree and 60-degree angles, I've got a little picture of the system up there in the upper right if you need to refer to it. The reason I chose those angles is simply because I can now do this decomposing into components, which is what I'm doing on this page, relatively simply just by understanding the properties of that you may remember from what's called a 30, 60, 90 right triangle. In a 30, 60, 90 right triangle, you may remember, you may not, but then I can just tell you again, that the side opposite the 30-degree angle is half the length of the hypotenuse. So I'm showing that there. If the hypotenuse has length 1, then that side is length 1/2. The short side has length 1/2. And knowing that, then you can work out from the Pythagorean theorem or just from remembering that the longer side has a length that is square root of 3/2 or 0.866. You can see that because if I square root of 3/2, I get 3/4. If I square 1/2, I get 1/4. I add 1/4 to 3/4, I get 1. I take the square root of 1 and I get 1. So that's just showing you that the Pythagorean theorem is satisfied in that case. And it's just using a special property. I haven't proven to you that the side opposite the 30-degree angle is 1/2, but it is. And you're just going to have to take my word for it this time. Okay, so I'm using that fact so that when I look, as I do now, to the right of the diagram on the left, there's the vector diagram on the left, but now I'm going to take each force in sequence. Force T1 first is that it's 50 pounds, 30 degrees above the horizontal to the left. And I can just use the properties of a 30, 60, 90 right triangle to see immediately that the upward component of that vector is 25 pounds, half the 50. And the leftward component is 0.866, or square root of 3 over 2, times the hypotenuse. Now, I've written them down below there in terms of trigonometric functions. I'm not going to worry about that. If you know your trigonometry, you can also find those components that way. But it's enough just to see that the properties of a 30, 60, 90 right triangle give you the 25 and the 43.3. And then the only other thing to be really, that's important to understand, is that horizontal component is in what I'm considering the negative x direction. So it's a negative 43.3 pounds. That's the component of that vector in the x direction. If I do the same thing with T2, I'm a little more handicapped by the fact that I don't know what T2 is. I know that T1 in magnitude is 50 pounds. I don't know what T1 is, but I do know that its horizontal component is positive now 1/2 T2, because that's the side opposite the 30-degree angle, and because it's directed to the right, it's positive. And I know that the vertical component is the square root of 3 over 2 times whatever T2 is. That's the vertical component. Oh, and I just realized I screwed up there. Sorry, that negative sign on the T2 cosine 60 degrees shouldn't be there. X that little negative sign on that middle diagram out. It's a positive component. I just copied and pasted, unfortunately, from the previous one. And then if I look at the weight force, that's easy. All of the weight force is in the negative y direction. It has no x component. The x component is 0. The y component is negative whatever the weight is. If the weight is 30 pounds, then the y component is negative w. W itself being a positive number, the y component is negative that number. These are the kinds of things that really screw up introductory students, is trying to keep their signs straight. And you need to come up with some way that works for you. Let me stop there for a moment, just a moment, see if there's any questions.
John, would you like to do a practice run, you and I?
Sure.
Like
Yeah.
I
Practice
want to
meaning
try it
what?
myself. I want to try myself to see if I understood what you're saying or not. So if I
Okay.
could draw the force diagram. So could you click on the link I attached the last one, the Jitsi one, so you can see my video?
Let me see here.
See if that works.
Join the meeting. I'm not going to give it access. Okay, let's see. I guess that's working.
Dark John is here. I
Okay,
can see
good. I
you.
see it. Yep.
Yeah, you see you. So okay, so you see the YouTube stream now. You see your course and you see your slides, right?
I'm seeing the Jitsi thing. Is that what
Yeah,
that
but
is?
what's
Okay.
on the
Yeah.
Jitsi? Can you, if you're not seeing it, double click on the scientific discourse. You will see a bigger. Are you on phone or on desktop?
No, I'm on desktop.
Okay, if you just double click on the scientific discourse, you should see.
Meaning when you say the scientific discourse, I'm
Because
not
I'm
sure what
running the
that means.
meeting as the scientific discourse.
Okay. All right.
Yeah.
Let's see.
If you click on my picture. By the way, everyone else is welcome to do the same.
Okay. Well, I mean, I'm looking at my slide 5
Yeah,
there. Is that what
great,
you want to?
great,
Yeah.
fantastic.
Yeah.
All right, so
Yeah.
now if I do this, hold up. You're supposed to see me with a picture
Okay.
of the ceiling and the thingy, right?
Right.
Great, fantastic. Let's see. So what should I do here first? All right. So I'm looking at this, and my intuition says this should fall down, or this should move right to left. What's step one? How should I go about this and say, well, here are all the forces?
Well, I'm not sure what you mean exactly. I mean, what
Well,
what I would
what I
do.
mean is I know gravity will act. How do you want me to do with gravity here? What should I do so that I can represent gravity here?
Okay, right.
Should I
So
just
what you
write something like this? Should I just write gravity like that?
right.
What's your recommendation here?
So if you wanted to indicate the forces on this diagram,
Mm-hmm.
I would probably draw a red arrow up and to the left, right along the T1 line, a red arrow up and to the right, right along the T2 line,
Right
and
here,
then yeah, right, like
and
that.
then
So that
right
would be
here.
the force T1, and that'd be the force T2, right, like that. And then there is a force, a downward force, and we're going to talk about this later. That's why I didn't really want to get into it now. There is a downward force acting somewhere. The weight force, it is downward. When we talk about torques, it's going to be important to know where it acts, and that's when we'll start talking about it. But if you wanted to put it on this diagram, it should just kind of be somewhere in the middle of the beam, kind of heading downward. And
Like
as
so.
we will see, it can't be in the middle of the beam, and that has to do with
Ah,
our. But that's what I would do at this point,
all
because
right.
all I'm doing is trying to show the forces.
Let's do that then.
And the fact that I don't know exactly where to draw it is part of, I should keep in mind, right? I'm going to draw it here, but I know that unlike the tension forces, I don't really know where that force is acting.
So
Yeah.
I'm just going to write a question mark here, and just to be clear, the y direction should be this one here. So I'm going to write I'm going to make a big vertical line. And I'm going to say this is my y direction. This is the one you want to choose, and
That's
then
what I chose, right?
yeah,
And
and
then the
then the one
horizontal
going to
x
the
to
right
the,
like that, and it'll be
that's
our
right.
x direction. Great.
That's right.
And so
But it is important to understand that that's arbitrary. It may seem obvious, but it is arbitrary, and in some situations it's useful to pick it in a different direction.
arbitrary meaning random, or arbitrary meaning we can do whatever we want with it?
Meaning you have to make a choice, but your
Mm-hmm.
choice can be anything you want it to be.
So I'm in control here. I can totally say y is downwards and x is to the left. No problem, right?
That's right.
And whatever it is that we choose, we're going to get the same answer. It doesn't matter.
That's right. It doesn't matter
Great.
what directions you choose. You'll get different equations, but those equations will have the same solutions.
All right. And
Yeah.
I'm not sure about these cosines and sines you have. Where did you get those?
Well, I kind of don't want to talk about that.
You
It's
don't want to
enough.
talk about,
It's
okay.
enough
I'll leave it then.
here.
I'll leave it. Okay.
Yeah,
I'll
it's
leave it.
enough here to just use the properties of a 30, 60, 90 right triangle. But for those who know trigonometry, they should be able to figure out why I said that, except for the mistake I made with the minus sign on that one
Okay, so we're not doing
slide.
projections yet.
Not doing what?
Vector projections.
Well, I'm not sure what you mean by that. That's exactly what I
I
consider
mean getting the
myself to
vector
be doing.
components on x and y. Isn't this what you did on the slide?
That's what I did on 5, right? I
Yeah.
found the components.
Great.
And I found them without trigonometry
without
because
trigonometry, without anything.
the triangle is such a simple triangle. I didn't need trigonometry. I mean, effectively, I'm doing trigonometry, but I don't need to use sines and cosines.
So if I were to try to do what you did, what I'm assuming you did is that there's a horizontal line here I'm drawing in black, right? And this is also the axis x, and I can do that because this line is parallel to the one we drew in the bottom, right? I can make this system whatever I want. Correct?
All of a sudden, I've lost your diagram. I don't know.
You
what
lost the diagram.
here.
I can see you still in the meeting.
I think maybe I closed it by mistake. Anyway,
okay.
Let's see. Yeah. I think maybe I won't go back there just now. Yeah.
So,
anyway, what you're saying is right. We could choose I could choose my x-axis to be
So I'm gonna
along
make,
T1,
yeah,
and
I'm
then
gonna make
T1 would have only an x component.
I'm going to make a copy of this. I'm zooming right in for those people following me. So I'm going to make a copy of this going to the right, this X, and another copy of this Y going way up. And again, I can do that because I'm just making a smaller copy of it, right? I'm changing nothing here. All of this is arbitrary. We could have made the original one, the black one I have drawn here. And let me just make a copy of this red one so that we can see exactly what's happening. And now, if this angle here is 60 degrees, I know that this angle here is 60 degrees as well. And this is because the two triangles are, the two angles are alternate. So this is a basic geometry fact here that these two angles are 60. And what I can do
So
here is, yeah.
right. So I'm a little worried. I don't know how many people in the clubhouse thing are actually doing the Jitsi thing. So I
I'm doing
don't
it.
want
I'm
to.
doing it for YouTube. I'm doing it for YouTube for self-containment.
Yeah. Okay.
So again, everybody's welcome to join. If you want to watch, it will be a lot easier for you to click on the video for just a minute, and then we can continue on Clubhouse. So again, I can draw this system wherever I want, and this side here, the one I'm drawing in blue now, this one here will be the x component of the tangent. Why? Because it's on the x-axis. And the one we drew vertically, and I'm making it in blue now, will be the y component. So these two vectors now, they make the same thing as the force along the line, along the rope. Why is
That's
that?
right. It's always worth understanding that if you take the x and the y component as directed vectors and add them the way you add vectors, you end up with the sum of those two components being the vector. It's really the vector is the sum of its vector components, right?
And why is it that I can do it? Because what I want really is not the summation of the distances. So of course, nobody doubts the fact that if you add the distance along x plus the distance along y, it's a bigger one than the red vector. And this confuses a lot of students and a lot of people who are being introduced to this. I'm not about finding the red distance here yet. What I'm really about is if I want the same effect, so this rope here that is hanging from the ceiling, its effect is equivalent to the effect of a small thing tugging to the right and a bigger thing tugging upwards. It's acting in the similar way. If you have two people, one tugging exactly to the right, perfectly along x, and another one tugging perfectly along y, they produce this effect with this angle. And
That's
this
right.
will
So,
help me
so
find the force I need to apply here, or the force that the rope is applying to get the main force along this rope. And if you do
right.
this work, and John doesn't want to get into it now, and so we will skip this, but this is exactly what the thought process. We're going to make another triangle here on this vector and find these two. And we're going to talk about the weight later because we're not really sure where it is now. But this is the main idea. I want to find things I can control. So I can't really know what's happening in the rope directly. But if I take two pieces, a piece on the x and a piece on the y, I know exactly what's happening because y is vertical. I can control that, and I can control if everything was x and y in my calculation, we can solve the system easily, and we will see how.
Right. So just to kind of re-summarize on slide 5, I've shown the three vectors that we identified and the directions of those vectors. The one that I actually know the magnitude of, the T1, is 50 pounds in that direction. And then to the right of that, I've shown sequentially taking each one of those vectors and breaking it down into how much it's to the right. T1 is negative 43.3 pounds to the right, and how much it's up. And T1 is 25 pounds up, positive 25 pounds up. I probably should have put a positive sign there. Whereas T2 is, the only thing I can say about it is that it's positive square root of 3 over 2 T2 it's positive square root of 3 over 2 times whatever, however big T2 is upward, and it's positive 1/2 of T2 to the right. Once again, that negative sign in the below the T2 thing shouldn't be there. Sorry about that. And then that the weight is effectively just whatever the weight is in the downward direction, negative that weight in the upward direction. So I identify those three things. And then I'm going to just, on the next slide, I'm just going to take what I found, all those three diagrams I repeat up there at the upper right of slide 6. And then I just apply the first condition, that the sum of the forces equals 0. That's three equations, one in the x direction, one in the y direction, and one in the z direction. But in this particular case, there's nothing going on in the z direction, which would be out of the page and into the page. There simply are no forces in that direction. So it's effectively just two meaningful equations. And the x equation says that the negative 43.3 pounds from T1 plus the plus 1/2 T2 from T2 have to add up to 0. And the y equation says that the plus 25 pounds from T1 plus the plus square root of 3 over 2 T2 from the rope on the right, plus the negative W. Notice I'm adding that component. The equation says add everything. That component is negative W, so I'm adding it to the other two. And when I add those all up, just like I did on the top, added those all up, I get 0. So I now have two relationships. And this is really a place to pause and understand what I've done. I've simply taken this system, I've said, this looks like a static equilibrium system. The relevant physics is sum of forces equals 0. So I go through the process of finding the forces, identifying them, breaking them into components in some cleverly chosen coordinate system. And then I just write out what that gives me. And at this point, I have two relationships between things that I do know and things that I don't. And the interesting thing in this case is that one of those relationships has only one unknown thing in it. So I can immediately solve that x equation has only T2 in it. So I can immediately solve that equation and get that T2 is 2 times 43.3 pounds or 86.6 pounds. So now I know what the tension is in the rope on the right. Now, I don't know what the professor was asking me to find, but whatever the professor was asking me to find when he gave me this problem on an exam, this is what I'm going to do because solving the problem will require me to simply apply the relevant physics principles. And that's what I'm done. So now I know T2, and now that I know T2, the second equation immediately tells me what the weight of the rod is. You can solve that equation for the weight, and you get that it's 25 pounds plus the square root of 3 over 2 times 86.6 pounds. And amazingly enough, that's 100 pounds. It's exactly 100 pounds. It works out to be, if you even if you put in the exact numbers there, you get that the weight of the rod is 100 pounds. So that's cool. Now I know those two things. If the professor had asked me what was the weight of the rod, I would be done. I'd say, it's 100 pounds. And I didn't do that by trying to find an equation that gives me the weight of the rod. I did it by looking at the physical situation and identifying a principle that was going to give me some relationships, and then keeping my fingers crossed that those relationships would end up finding me the thing that I wanted to find. But maybe that's not what the professor asked for, because we're going to see there's one more thing the professor could have asked for. And if I were that professor, that's the thing I would have asked for, because it's the one thing that doesn't come quite as easily.
John, it might be worth just for people who don't like the mathematics saying you can do this geometrically incredibly easily. You just put each of the triangles tip to tail, and you just measure the length of the third side, right? Final, so the fourth side, the final side.
That's right. If you I don't do that specifically actually, but it is true that if you understand vector addition, the way you draw one vector and then you take the next vector and you move it, you transport it without rotating it or changing its length, so that its tip is at the tail of its tail is at the tip of the first vector, and then you do that for the third vector, and if there's a fourth vector, you do it for the fourth vector. The net result of adding any number of vectors is, once you've done that, is just to draw a so-called resultant vector from the original tail to the final tip. And if you know those vectors add up to 0, then you have to draw them in such a way that they form this triangle. And you're right, Ben. I should have actually drawn
Well,
that, because
I
if
just
you
think for
do
people who don't
that,
want to get a calculator out, they can, with just a ruler and a protractor on a bit of paper, they can solve this problem. They just
that's
draw a
right.
line that's 50 something, call it 50 centimeters, 50 millimeters for the T1. They draw another line for T2 at the angle, but they don't know the exact length. And then they would draw the resultant weight and direction and just measure. They just got to measure 30
That's right.
degrees, 60 degrees and one length, and they can get everything. Yeah.
That's right. What you'll see if you do draw that vector diagram is that it
No
forms
calculator.
a 30, 60, 90 right triangle, with the 50-pound weight being the short side of that thing, and with the weight being the hypotenuse. So you kind of immediately see that the weight is 100 pounds.
And the other thing here, you've got three forces, but I always, when I ever look at a structure, I always remind myself that basically all static equilibrium comes about, I think, because of three forces. There's often a lot more involved, but you can always identify a triangle of forces in anything. If you're holding your arm out to the side, you'll be a triangle of forces. It's going to be two forces around in your shoulder somewhere, around the pivot, and one force of gravity. I think you can always identify, because it's the only if taking the geometric thing a step further, a triangle is the only stable geometric shape, if you think about it. If you consider the pivots of a triangle, the points of the triangle as hinges or pivots, there's no other geometric shape that is stable if the hinges
Well,
are loose.
I'm not
So if you have a
sure what you mean
square,
exactly, because I could, for instance, in this case, I could have had another string attached to the midpoint of the
yeah,
rod,
you can
pulling
have as
up at
many.
60 degrees.
You can have as many as you like, of course, but you can always resolve it down to a stable triangle. You can always collapse it down to a stable triangle. If you think about it structurally, if you get three, lolly sticks or ice cream sticks and kind of stick them together, a triangle is solid. It can't move anywhere. There's only one way that a triangle can be formed. But the moment you've got a square, for example, that can be made into a parallelogram, and any other geometric shape where each of the points where they meet can pivot is no longer stable. So whenever you look at any structure, you can always identify triangles inside that structure. There must be a force triangle in there somewhere. It won't stay still. A minimum of a triangle of forces, but it's also can always be boiled down to a triangle of forces, I think.
I guess I'm not entirely sure what you mean, but maybe we can
Yeah, we could do that offline. It's a deeper observation about it. Yeah.
Yeah.
But that's
Yeah.
okay. Yeah, we'll do that offline. No, it's not to confuse people. But the take home really is that you can do all of what you've just done just with, if you can use a ruler and
Certainly
a
in this
protractor.
case, this is such a simple case that one could do it without really any math at all, just, geometrically. But this is a more general technique that will get you through situations that don't quite work out so simply.
Yeah.
Okay, let's see. So I think we've applied the first condition. We found those two forces, but there is another condition, the torque equation, which we haven't used yet. So a word on slide 7 about torques. Torques involve applying forces, one, at some point of application. So there's terminology here that's worth getting down. Torques involve applying a force at a point of application, that is some distance from a pivot point. And we'll talk about those two things. With a component. There should be a component of the force that is perpendicular to the line drawn from the pivot point to the point of application. Now, this is fancy, esoteric way of saying stuff that we all understand. When you want to free a very stuck bolt, you get the longest wrench you can find, and you hold that wrench out at the end of the wrench, getting as far away from the nut that you're trying to break or whatever, trying to free as you can. And then you don't push toward the nut, and you don't pull the wrench away. You push on the wrench at right angles to the line drawn from the nut out to the end of the wrench, right? You need some, there's language like you need a large lever arm, and you need to apply a component of the force. Any component of the force that you apply along that lever arm doesn't help you. It's only components of forces that you apply perpendicular to the lever arm that help you. And so that diagram down at the bottom left is just to show that. You've got a pivot point. Suppose that's a nut you're trying to turn. You've got a distance away from it, maybe call that a wrench, and you apply the force at the point of application out there, a distance r away, with some force. And part of the force that's shown there doesn't really help you. The part that's horizontal in this case, the part that's parallel to r. But the part of that force that's perpendicular to r is the part that gives you the torque. And the torque is indeed just the product of that distance away with the perpendicular component. And there's other ways that you can calculate torques as well. We may get into them at another time, but this is for now probably the simplest way to think about it. You simply, and I didn't say it here, I should have said, the torque is the product of that distance from the point of application to the pivot point times the perpendicular component of the force, the part of the force that actually gives you some torque, that twisting force. And then because we actually have to balance torques, we have to understand something about directions, which in this case we can think of just in terms of positive and negative twisting components. In a two-dimensional example like this, an object can only turn clockwise or counterclockwise. A more general rotation, I couldn't simply say clockwise or counterclockwise. I'd have to talk about how much something turns around the z-axis, how much something turns around the x-axis, how much something turns around the y-axis. In this case, it's enough simply to ask, is the thing as shown going to rotate clockwise or counterclockwise? And we usually do that using what's called the right hand rule, which is shown in the diagram on the left there. If your fingers twist in the direction of the turning of the torque, if you want the twisting force, then your thumb is an indication of the actual direction of the torque that we apply. It's a weird thing. We say that the vector torque is along the axis of the turn, and it's in the direction that your right thumb points when your right fingers twist in the direction of the twisting force. So in the case of that diagram on the left there, that would be if I took my right hand and I oriented it so that my fingers are in the direction of the twist, which in this case would be counterclockwise, my right thumb would be pointing at me, and we call that a positive torque because the thumb is pointing out of the page when I do that with my fingers. Now that's just a convention. You can choose another convention if you want. There's no problem, but you have to be consistent about it. And the convention is to choose it in that way. So that's what we'll use. That's this whole torque thing and twisting forces and vectors along axes and so on is a weird thing. It's a pure mathematical convention. We use it because it works. And because, in fact, if you wanted to represent a turn by a vector, it turns out you can't do it except by picking the vector along the axis. There's no unambiguous way to determine that rotation except by choosing the direction along the axis. You might think about that and see if you can come up with a better way to do it. Comments before we move on and actually apply this? Okay, let's do it. On slide 8, so we're going to apply the second condition. To apply the second condition, we need first to pick an arbitrary, once again, completely arbitrary, but clever pivot point. Now, the pivot point that I'm choosing is not particularly clever, but it's a little bit clever. I'm going to choose as my pivot point. Here's what you have to do. You have to pick a pivot point around which the object is not rotating, because the second condition says that the torques add up to 0 because it's not rotating. It's not changing its rotation is really what it's doing. In this case, that means you can pick any pivot point you want, because this object is not rotating around any whatever pivot point you choose. The object is not rotating around that pivot point. So you're free to choose any pivot point you want, and we'll get back to that on the penultimate slide. That's the next one. I'm going to choose the pivot point to be the left end of the rod. Okay, and then what I need to do is I need to find the distances to the points of application of the three forces and multiply those by the perpendicular components of the forces to get my torques. Now, the reason that choice of pivot point is clever is because it makes one of the torques 0, because the point of application of T1 is the pivot point. There's no way that T1 can provide a torque around the pivot point. To apply a torque, I need to apply the force at some distance from the pivot point. And I'm applying that force right at the pivot point. You can never turn something by pushing on its axis. You have to get away from the axis, even if it's only gripping the thing out, at a cylinder at some distance from its axis. So T1 doesn't provide any torque. I have only two torques. The torque due to T2, I'm some distance. Notice that I haven't told you even what the length of the rod is. So and this is another important lesson when you're working physics problems. You have to be willing to say, oh, I don't know what that is. Well, give it a letter and get on with it. So in this case, I'm just going to call capital L, I'm going to call the length of the rod capital L, just so I have something to use. And the torque then, due to the force of the rope on the right, T2, is the length L times 75 pounds, which is the component as I've worked out up there using the 30, 60, 90 right triangle thing. Remember, T2 was 86.6 pounds. That side I'm trying to find, the perpendicular side of that, is the long side of the 30, 60, 90 right triangle. So it's square root of 3 over 2 times the 86.6 pounds. That makes it 75 pounds. So 75 pounds times L, and is that positive or negative? Let's see, I get out my right hand. I see that that force is going to want to make it rotate counterclockwise around the pivot. And so that's a positive torque of L times 75 pounds. The weight force, this is where we get into the difficulties of weight. It turns out, and we can talk about this, and we should talk about this, but I won't force us to. It turns out that you can treat weight forces when you have a uniform gravitational field, like we do basically on Earth. You can treat a weight force as if all of it acts at the so-called center of gravity, which is the same thing as the center of mass. So what I'm doing in this diagram is just showing that the distance from the pivot point to the center of mass, which I don't know, you might be tempted to say, well, that's L over 2. But I didn't tell you that it was a uniform bar And as we're going to see, it isn't a uniform bar. So I'm just going to call that distance d. And if I multiply that distance d by all of the weight, because notice all of it is perpendicular to that distance, I get d times the weight, which is 100 pounds. So adding up all the torques, I get 0 from T1, 0 times 50 pounds. I get negative d times 100 pounds. That's the negative torque due to the weight, the torque that I would have to point my right thumb into the page to get my fingers to twist in the right direction. And then I get the positive L times 75 pounds. So I get a new equation there. And now I can stop and look at it and see what I get from that. And all you get from that equation is that D is 3/4 of L. When you simply solve that equation, you could solve that equation for lots of different things. But if I solve that equation for D, what I find is that D is 3/4 of L, meaning that the center of mass of that rod is way over there on the right side of the rod. It's a distance 3/4 of the way from the left end to the right end. And that means, of course, that has to translate somehow into that rod being heavier over there on the right side than it is on the left side. And that is, of course, what accounts for the weirdness that we saw when we examined our intuition back at the very beginning there. Now, there's a lot of torques are difficult. We went through it very quickly here, and we might want to talk about different ways of thinking about torques, and there are different ways of thinking about them in the discussion. But let me just stop briefly and see if there's any comments or questions on that slide.
So I'm going to share something and also make a comment to simplify talk. The simplifying comment is just think about a seesaw. I think that's the thing where we've all had intuition of talks as kids, right? Your kid sits on the end of the seesaw, your mum or dad has to sit closer to the pivot point in order to balance the kid. That essentially talks boil down to that, right?
Right, and this is
Static
what's
torque
called, what is this, a
equilibriums.
first or second class machine, really, with the pivot point chosen where it is? I think is that what we call a second
Well,
class machine?
you're talking about types of levers. There's lever classes.
Levers, right.
I will. I did a YouTube short on that. I'll share that in the chat now because I already
Good,
did that. But then
right.
the other thing was, the day that I realized my dad wasn't going to be the person to teach me physics was when I learned about torques, and then I had a conversation with him about screwdrivers, and I said, hey, a longer screwdriver doesn't actually help you undo a screw. It's the thicker the handle that helps,
Hmm.
or you have to stick a ratchet on it. He goes, no, of course a longer screwdriver helps. I'm like, well, it doesn't, and then we had a bit of an argument, and I just
It's
got it. I've
because
got
they usually have bigger handles, right?
Yeah, exactly. I've actually got 3 videos on talk, so I'll post those in the chat. What is talk in physics? A practical example with a ridiculously large toolkit, and then I've got a third one where I think I've still got the third one, where we talk about the classes of levers. So I'll find those and put them all in the chat in a sec.
Yeah, good. Yeah, Ben is the master of torque. I know I think there's even a bite of physics or two that you've done for me that talks about this kind of thing too, right? Anyway,
Talks
he's
about
looking for
talk.
links.
Well, no, it's okay. There was it's because I had to modify a game engine to actually do inertia tensors properly. So that's why I got well into talk. But let's not throw swear words around in this session.
Anyway, if you look at the diagram the way I've shown it and really think about if there really were literally a pivot point where I've shown it, then you can see this is kind of a wheelbarrow thing. You've got a load in the middle, and it's maybe a heavy load, but because you're back further away than that, you're able to lift that wheelbarrow with a smaller force than all the stuff that's in the wheelbarrow, and then maybe roll it forward or something like this. So it's that kind of an arrangement, an upward force behind a downward force that's a little bigger. The two things then providing the same torque, because a smaller force at a larger distance can balance a larger force at a smaller distance. And that's really what you're looking at. Okay, so the final thing before just my concluding words is just to point out that you can be with torques. You can actually solve, in fact, any problem like this using nothing but torques. You can write out the torque equation using three different pivot points and get all three relationships that I got using getting two of them from the force equation and one of them from the torque equation. This particular pivot point is really a nice one because it immediately, if I do this, what I'm going to do is I'm going to take what's called the line of action of T1 and the line of action of T2, and I'm just going to extend those lines until they intersect. And they will obviously intersect somewhere below the bar. And what if I choose that as my pivot point? If I choose that as my pivot point, then neither T1 nor T2 can provide any torque at all because the point of application, because the component of those forces is zero perpendicular to the line, the dotted line from the pivot point to the point of application. Neither one provides any torque around that pivot point. Therefore, if the torques are going to balance, the torque due to the weight will also have to be zero. If it's not zero, then there will be non-zero torque because it's the only force left, and the other two we know are zero. So I know that the line of action of the weight force has to also go through that pivot point. Excuse me. And if you look at the diagram that I've drawn there, all those dotted lines on the bottom are just three 30, 60, 90 right triangles. There's a big 30, 60, 90 right triangle. There's a kind of an intermediate 30, 60, 90 right triangle on the left. And there's a small 30, 60, 90 right triangle on the right. And if you just write out what all the relationships are, I'm not going to go through it here, but you can show that dotted line, the vertical dotted line, intersects the bar 3/4 of the way from the left to the right end, just like we've already shown. So I can get that same result geometrically as in a similar way to what Ben was talking about earlier, without even having to do any numbers. I don't need any numbers at all. I just need those angles, and it tells me immediately that the center of mass of the rod is 3/4 of the way over to the right. So that's a often a clever thing, and you might be tempted to say, but how can you choose that as the pivot point? That's not even on the bar. But it doesn't matter because the torques on that bar are zero around any pivot point you want to choose. That bar is not rotating around any pivot point. Pivot points on it, pivot points not on it. So you can actually do that kind of thing.
You
Okay,
can
so
also solve these.
go ahead.
You could also solve this geometrically as well, John. You can effectively do all your projections if you're off, if you're not 90 degrees, just on a bit of paper, you just project sideways till you get to the perpendicular. And then you can just multiply the distance from the pivot by the line, the length of the force line. I mean, okay, you have to do a multiplication. But apart from that, you don't even have to do a multiplication. You can do it by making rectangles. If you do it on graph paper, you can just make rectangles where the distance from, say, the center of the seesaw to the one person sitting is one side of a rectangle. And then their weight is represented by the other side of the rectangle, going up or down, doesn't really matter. And then you just make sure that both rectangles have the same number of squares in them on either side of the pivot. And you can do that for any number of torques at any distance, as long as they're at 90
It's
degrees. So you can just stack up blocks.
my only caution about anything like that, and this is a very special case that we've been dealing with today. My only caution is certainly one that I always told students. Students would often attempt to say, well, we could say this, and then they say we could say this, and it turns out the thing that they think you could say just isn't true. So it's always a good idea when you're learning this stuff to really follow the explicit procedures. When you're finding forces, really literally draw a dotted line around the thing, go around that dotted line with your pencil and look for anything that penetrates it to find things that touch your system, etc. Write out the component equations, put in just do it, and then start to notice and get better at the shortcuts later. Because if you apply nothing but the shortcuts at the beginning, you'll just get them wrong, and you won't learn how to do. Sorry, you won't learn how to do problems that are for which there are no shortcuts. And well, there's always shortcuts of a form, but you really need to know how to do it exactly right, and then you can be cleverer as you
Yeah,
move on.
the most general way. I agree with that. There's no shortcut to the shortcuts.
Yeah,
You spot the shortcuts. Yeah, okay. I think that's
and they're
good
good.
advice.
The short once you then find the shortcuts yourself, your intuition, you gain
But I,
intuition from seeing those
this is
shortcuts.
a bit like asking ChatGPT to answer a calculation question for you. The thing is that if you're going to use a shortcut, if you're not 100% sure that the shortcut's right, you need to know how to do it the long way to prove that your shortcut works again. Basically, it's how long since I last used the shortcut, and am I still 100% sure it works? A similar sort of thing with asking ChatGPT to do a physics question for you. It's going to get it wrong most of the time. So if you can't do it from first principles yourself, you've got a problem. So I think that's a really important that you learn you earn the right to do the shortcuts by doing it the
Right.
hard way enough times that you recognize for sure when a shortcut applies. And if someone stops you and says, "Hey, are you sure you can use that shortcut?" You can go, "Okay, well, let's go around the houses and show you how this is the same as the shortcut."
Yeah, that's right. Yeah, you need to be able to back it up with the long cut. So that's it. Just closing words, and this is really, I think, if there's one lesson that I want to leave my physics students with, it really is. I think this is the prime lesson, and it's really a hard one for students to learn because it does require discipline. It requires getting rid of a mindset that is hammered into students in elementary school and high school, and that is find a formula that gives you the thing the problem asks for. That is not the way you do a physics problem. Um, you don't search for a formula that gives the thing problem asks you to find. I've had students where a problem asks them to find the velocity of something, and they find a formula that says v equals e times d or something like, e times d, which is an equation from electrostatics that says the voltage is equal to the electric field times the distance that you go along the electric field. But there's a v in it, right? And they're being asked to find a velocity, and so I've got the equation, right? And then now they're looking for E and D. I mean, I'm kind of, this doesn't happen very often, but when you search for equations that have the thing you're trying to find in them, you're almost always going to get the problem wrong. That's not the way you do physics problems. The way you do a physics problem is you look at the situation that's being presented to you, and number one, you identify relevant, broadly general physics principles. That is step one. Once you've identified the principles, then you apply those principles to the situation to get equations. These equations may or may not have the thing you're being asked to find in them, but those equations will give you information that relates things that you do know. There's going to be some things that are in the problem statement. It relates those things to things that you don't know. There's going to be variables, there's going to be letters in the equation that stand for things that you don't know. And you may gather, because depending on what principles you've found, you may gather 2 or 3 or 4 or 5 or 6 equations relating things you know to things you don't know. And those equations come directly from applying those relevant principles to the problem. You're not, if you find yourself worrying about whether the thing you're trying to find is in there, you're already making a mistake. You get these equations once you've satisfied yourself, at least kind of preliminarily satisfied yourself that you think maybe you've found all of the relevant principles, then you can take a look at those equations. And that's kind of what we did here. We applied the force balance equation, and we found out that from those we could find the tension in the second rope and the weight of the beam. Okay, good. I don't care if the problem asked for that. Now I know more stuff. Now I know more things than were in the problem statement. And if one of the things I now know is what the question was asking for, then I'm done and I can move on to the next problem on the exam or whatever it is. But if it's not, well, then I need to find another physics relationship, like maybe the torque balance one, like we did here, and get whatever its relationship did. And that's the way we do it. We use those equations to find things you don't know, expanding the number of things that you do know. And then you just continue that process until a set of all the things that you now know has expanded so much that it includes the thing you were being asked to find. And what a diabolical physics professor will do in designing an exam question is to ask you for the one thing that he or she knows is probably going to be the last thing that you find. There's not going to be one of the things that you can find without applying all of the relevant physics. It's probably going to be the thing that requires you actually to identify all of the relevant physics. It'll be the last thing that you add to that list. But the moment you find yourself, looking for an equation that has the thing that you want to find in it, rather than just identifying principles, applying them, and seeing what happens, you're not doing physics. And when a physics student really learns that, it's an incredibly empowering thing. All you're doing in physics is applying physics principles and seeing how the cookie crumbles from there.
So John, this
kind
is
of
this.
my closing line.
I think Hiro wanted to go because
Yeah.
I've been more than him. Go ahead, Hiro.
Yeah, so on the topic of diabolical physics professors, I'm a little annoyed, but I guess I'm more annoyed at myself because this is a mistake I've made often on physics tests, which is I add in an assumption that wasn't actually in the question, and so like I look at this completely differently than you did, but I also think maybe you purposely were ambiguous
Was
about some.
diabolical.
You were a little diabolical. So like you know, I didn't hear you explicitly state, but I guess you did that this system was in equilibrium. Like that was definitely in equilibrium.
Oh,
But I think that was the setup. But
I
also
think
the
I
way
said,
I
go
think
ahead.
you did say it, and I just
I think I
skipped over
said,
it.
well, I think the way I put it was, it is, a straight bar is held in a horizontal orientation by two ropes. And so I probably could have said it more explicitly.
You
But you
you
can't
also
hold
drew
something in a horizontal
you also drew
orientation.
that bar in a way to sort of suggest that the weight was equally distributed. I mean, you could have explicitly
Ah, that's
said
true.
you could have drawn like a wobbly thing and and made it clear that the center of
That's
gravity. So
fair.
so
That's
what I
really
so
fair.
what I did, but I also kind of made that assumption in my head. I'm like, oh, the weight's evenly distributed. The center of gravity's in the middle. I so what I did both triangles on each side and calculated the horizontal components, what they must be, and showed that the left side was 43.3 and the right side was 14.4, and that this thing would definitely swing to the left. But I added that assumption in there. So that's actually like a life lesson there. Like look at
So
the question,
hold on a second.
don't
Explain to me
assume
what you. I'm
anything.
not.
Yeah, I'm
Can
not sure how
you
you
go
get to
back
it.
and tell
I'm not
me
sure how you
exactly
get
what
to
you
it
did?
moving.
Because I didn't quite
Well,
follow
I mean,
that.
I you have a triangle on each side. You can presume that the if the weight was evenly distributed, that the weight would be the same on both. So you have the vertical component is going to be the same.
Ah,
You have the tension on one side, so you can solve for the weight of the thing, and then on the right side, now you have the weight. You have half the
right.
weight
I
on
get
that
it.
on each side, and you can solve for the horizontal component on each side. So that's what I did, and I'm like, aha! So therefore, this is not an equilibrium, but I sort of missed the plot.
Yeah.
No,
Okay.
but
but
That's
in a
really
way,
good.
but in
That,
exactly the way the diabolical physics professors are trying to get you to lose the plot. So this
but
is
you
why
know
I
what?
switched to
I mean,
math.
No, that's really interesting, Andy. I didn't understand. Yeah, so you were saying that the vertical components of T1 and T2 had to be the same, and then you went from there to find out how much
Yes.
out of balance it was horizontally, and that's totally legitimate. And I think the best comment you made, I think I would not have. I think my statement was fine in terms of saying the straight bar is held in a horizontal orientation by two ropes, blah blah blah. But I think that yeah, drawing the bar as non-lumpy, that's misleading. That's kind of actively misleading. And I think if I had done that on an exam, I would probably, number one, I'd probably catch it before actually, printing it out and giving it. But if I hadn't, I would feel very bad about it, and I would do something to atone.
Can
But
I
I, th-
can
I
I ask
think that,
about that? Sorry, Ben, go ahead.
well, I was just going to say, I think the second thing that comes in with what you did there, Hero, is I think you're then also tacitly making the assumption that the tension in the two strings was the same, were you, or something?
No,
No,
definitely not.
uh,
You weren't
just
doing
the
that. Okay.
component, the vertical components.
Yeah.
Yeah. No, that's right. That's fair. I didn't
But why
think
would you make any
about
other
that.
assumption apart from, sorry, why would you draw it in wobbly in future, John? I don't have that connection.
I would draw it all wobbly, not to allow a student to just assume that the center of mass was at the center of the bar, because I didn't
Okay.
say anything about. I did say, I was careful to say, in fact, that it was straight, right? Not uniform. But that's a little overly diabolical, especially when combined with a picture that shows it as uniform.
You also place the W right in the middle.
Yeah, and yeah, I don't feel as much need to atone for that. But you're right.
No, but I mean, I sort of feel like as the student, my job is to not make any assumptions. Like this is always true in like geometry, right? Like you know, you know, two lines can look parallel. That doesn't mean they're parallel, or they can look like they're right angles. That doesn't mean they're right angles unless there's a little symbol there. So
Right.
you have to fight these intuitions a lot. But I went with my
That's really
intuition
true. I
and
mean,
kept
that's really a
going
good
and went to the wrong
comment.
place. So there's a good lesson there. You like in a way the teacher is allowed to be a little devious to test their students' ability to fight their intuitions,
Right.
bad intuitions. So it's all good, but that's
Well,
the direction
but
I
it really
went.
is. I mean,
Yeah.
your comment is really good, because that is a mistake that students make, is just as that kind of thing. Oh, those look perpendicular. They are perpendicular, right? You just, there are things like that which are not the professor's fault, which are things that students do make assumptions about things that are completely unwarranted. The assumption that this bar is uniform, I would call not completely unwarranted, because I've shown it as being very uniform. So that's fair. I mean, I think I would never, I certainly wouldn't draw it like if I were to draw it properly, I probably would make it kind of thin at the left end and thicker at the right end. I would not want to do that, because it kind of gives away the farm, right? But I should at least make it clear, maybe say a not necessarily uniform bar, or show it as kind of lumpy and non-uniform, etc. But yeah,
Can I,
no, these are really and all of the things that you do. For instance, in this problem, the fact that I have those ropes attached to the ceiling, and the ceiling is itself horizontal, is it doesn't actually give you any information that's useful. But a lot of people will, for instance, they might look at the ropes themselves and assume that the tension on the this is effectively what you did, Andy, was to solve as if the lengths of the ropes were the magnitudes of the tension, because of course the vertical components of those ropes are the same. And so what you would have found was essentially a ratio of forces that's the same as the ratio of the lengths of those ropes. and you don't want to have to make that assumption. You wouldn't have, well, I don't know. It's interesting to think what you, in your method, if I had attached those ropes at different altitudes but kept the angles the same, presumably you still would have done the same thing, but it's kind of related to, your method is kind of related to a mistake that somebody could make if they think the lengths of the ropes are themselves the forces.
So, John, the thing about the uniformness of its mass, if it's a rigid body, from the force equilibrium point of view, it makes no difference where its center of mass is, obviously.
From the translational equilibrium, right?
Yeah, from the translation,
Yeah,
it's obvious immediately from that, and you have to look more carefully to work out whether it is or isn't from a torque point of view, but not much more
right.
carefully.
Yeah, no, that's
So,
right.
so that's
The
one of these sort of shortcuts where the teacher's trying to, you could have drawn it wobbly, and then I think our job as a student also is to not be baited into a rote method of doing things, such as had you drawn the roof as sloping, makes no difference, but could draw you down a different line. It just reminds me of, I think I've mentioned it before, but there was a summer school I went on. It was a mathematical modeling summer school, and they did this thing where there was a skier going down a frictionless slope with no air friction, and the idea was that they need to get to the bottom of the slope as quick as possible, but at some point they need to go over a jump. How much should they try and push off the jump? Should they try and jump high in the air or try and stay close to the slope? That was the question. It was supposed to spend 2 days working
mm,
out. And the reason it would have taken 2 days is because most people would have drawn their coordinate system, X and Y, horizontal and vertical. But I just looked at that and said, it's ridiculous, because if you draw the coordinate system along the slope and perpendicular to the slope, you just told me there are no forces acting along the slope. Therefore, it makes no difference how high you jumped. You've just
well, but
written off the only two.
it depends a little bit on which way you push at the top of the jump, doesn't it?
Perpendicular. They were saying you push perpendicular to the slope, not to the.
To the
I mean, it
slope.
wasn't actually a
Okay.
jump. It was just you just jump yourself with your legs. There was no jump in the slope. If you see what I mean, the slope was just a slope. It was just a line.
Oh, I see.
You just push with your legs, and
Oh,
like
I
how
see.
high
Yeah.
you had to jump, but how high. And I'm like, it doesn't matter. It obviously doesn't matter. Just put your coordinates down the slope. You've ruled out all forces along the slope. It makes no difference. And that, of course, was the answer. Now, the the problem with that was they then told me to do the problem with air resistance, which was an absolute pain in the ass in comparison.
And is it a frictionless snow?
It was a slick, frictionless slope and no air resistance. So
Yeah.
obviously, it didn't matter how
Right.
high you jump.
Right.
But I say obviously, but that's one of those shortcut things. But what you're doing there is you're moving the coordinate system to match the symmetry of the problem, and then making your life a lot easier. What they wanted you to do is get knotted up in equations, and if you did the equations right, everything would cancel out, and you'd still get the same answer. And since that, I'm always on guard for, let's spend an uncomfortable amount of time looking at this and making sure we do it correctly in the right space, in the right symmetry, with the right type of mathematics, so that we don't knot ourselves up in circle to come up with an obvious answer. And that, I
Mm-hmm.
don't know if that's real physics. I mean, you were saying earlier that the physics isn't like applying the formulas; it's looking at the problem and deciding where well, you weren't saying this, but what I was getting from it is deciding where the boundaries of the problem are. One of the biggest things is what is the system you're
What
analyzing, and
matters
what's
is.
outside the system. What matters, what doesn't matter. That's the really hard bit.
Mm-hmm.
And I'm not really sure whether it's something you want to be teaching people really early on, to spend a lot of time thinking about what matters, what doesn't, boundaries of systems, coordinate systems in use, etc., or whether you earn the right for that after doing a load of problems. I'm not really sure which way round, but I don't know. Certainly for my kids, I wouldn't want to have to go through the drudgery of the mathematics when they can just make a simplifying assumption like that.
That reminds me of an ad when I was in engineering. I think it was from National Semiconductor, and it was similar to the problem that John posted. It had two uneven bars and a line in between them, and there was like a juggler hanging from the line, and the question was, find X. And the interesting thing about it was, I actually, when you try to actually do the math, it takes you down this rabbit hole of equations
So,
that
Carlos, can
perhaps,
I just to understand
yeah,
the problem a little more?
yeah,
So the rope is a loose rope hanging between different height bars,
yeah,
and you want to find the place that you kind of slide to if you're if you're like attached to it by a pulley maybe or something? Is that what you're
No,
thinking?
it showed a, it was like a circus. It was like a circus cartoon, right? And it showed two poles, like you said, of different heights, right? And they had somebody hanging down from the wire, and they wanted you to find the distance between the two poles.
Yeah,
And you had
but I mean, but you need more information. Is the person hanging? Is a person attached to the rope by something that will slide along the rope to the place where it won't slide anymore, or what? There's
yeah, I
something
think
missing in the problem
they,
statement.
they didn't give you that, but the assumption was that he was rigidly connected to the rope, and you had to find the distance between the two poles. But what was really interesting was what it said. It said many engineers overcomplicate things when the answer is right in front of them, right? And I was working on the problem. I started going down the equation aisle like they wanted you to, right? They wanted you to start doing equations, and then I quickly realized that the only way that the length of that line could be satisfied is if the two poles were right next to each other and x was 0. In other words,
Did they tell it? Did they tell
it
you
said
what the
not to
length of the
scale.
rope was?
It said not to scale, by the way. Yes, you could figure out the length of the rope, right? And once you figured that out, you would
Yeah,
realize that it added up to 0. The only way that
right.
length could be satisfied was if the two poles were right next to each other. What's interesting is I gave it to, I was working at General Dynamics, I gave it to like 5 engineers. I probably wasted around, I don't know, $100,000 of government money because uh, they
Thank you very
spent
much.
like weeks trying to solve this problem. It took me about 15 minutes once I realized that that was the problem, that X was 0.
Can you can you send me the exact problem statement? It'd be fun to
Yes,
spend
I
a couple
will.
This
moments
is a
with you.
famous
Yeah.
interview problem.
Is it? You've
Yeah,
seen it
it's like
too?
one of these problems that like sometimes you got to realize like there's no way they want me to do it this way. Like there's got to be, oh yeah, just add up the rope and add up yeah, there's the poles have to be right next to each other.
But it took me
And
a
And
little
if
in
while
you
to
that
figure it
case
out.
the calculation is very simple.
and if you
Right.
do go down the math, sorry, Carlos, go ahead.
Yeah, if you do go down the math puzzle, you're solving multiple equations, and
Right.
perhaps
Yeah,
it's
you also
solvable. But
yeah, but then what tends to happen is you with something like that is that you need to be really careful about things like divide by zeros or you square root and you get a
Right.
negative. Do you account for the fact that the square root of 4 is plus or minus 2, and these sorts of things? Because when you write out the formulas, a mathematician and physicists are a little bit more slack than a mathematician about writing in the margin. But this transformational, this step I've just made only applies for x does not equal 0 or for positive integers or whatever. A mathematician will always write that out. I don't think physicists always are quite as good about that, are
well,
they, John?
remember,
It's like as
this
in
was
being
this
really
was an
careful.
ad. This
And
was
that's
an
where
ad
that's
by
where your
National
get slipped, I think.
Semiconductor. They were intentionally trying to screw with engineers, right? That ad was intentionally designed to screw with engineers with analysis paralysis. And of course, I saw the ad and I'm like, because it said, and if you want the answer, give us a call. And I'm like, it will be a cold day in hell. I call them. I'm like, there's no way in hell I'm ever going to call them.
Well, I
And
really want to see this problem statement, especially now that I know that it's a common thing. Because who knows? I may need a job. Uh, but it's really that is really interesting. It's got to how exactly it's stated matters so much. To just kind of seeing that
I've seen
solution.
something similar,
Anyway,
John, where you just say, look, there's a plumb bob hanging, for example. Just imagine a plumb bob, anything hanging on a string, and you push somewhere along that string sideways. What is the what is the it's not it isn't. I'm making up as I go along. I know it's not going to work like this because I'm trying to get to infinite force in the middle of a string for the initial deflection, but it's not going to work with that particular problem statement. I'd have to think about how to lay it up. So I'll think about it and then prose it rather than
well,
prosing it as I
I
think about
had
it.
thought about a similar problem. I had thought about making this saying something like a 10-meter long bar um, is attached to the ceiling by oh no, how did I do it? Somehow I wanted to end up having the situation that it would have to be hanging from entirely from one rope, and the other rope's attached to the other end, but that the beam ends up just hanging vertically, and there essentially can't be any tension. Oh, I don't know. No, now I'm saying it wrong.
You're doing the same thing I
Uh,
just did. Sorry. Just,
yeah, yeah. So
let's try and work out
anyway,
a physics problem live before we finish thinking about
yeah,
it,
I
and
can't. I shouldn't have done that. But there's lots of whenever you start doing this, then it depends. If you make the problem actually depend on the length of the ropes by really making the points of attachment matter, as you were saying, Carlos. That's. I was trying to come up with something like that at first to do, but I
And the
just
hint,
I settled on that.
really the hint was what, it wasn't even a hint. It was like a little asterisk at the bottom that said, this is not to scale. And as soon as I saw that, I was like, okay, they put that for a reason, obviously. And that's when I started, that was like the hint that I needed to say that I was going down the wrong path. Plus, engineers overcomplicate things. That was like another huge hint to not do math.
often they'll put this is
It's
not to scale just to stop you trying to measure it off with a ruler, like, that as well. So it can be more innocent than that. And I think the point about going down the mathematical route is if you do it really carefully, you'll be okay. You'll still find out that either the equations you're trying to use don't apply in this circumstance, or that you get L equals 0 or D equals 0 or whatever. But you have to be very careful at each step, because we often make assumptions in steps when we divide through by things. Let's just divide both sides of this equation by x. Fine. You should really write in the margin x does not equal 0 when you do that. And I'm not sure physicists always do that.
I would love to find the original ad because it was long time ago before, when internet was even just starting. But that would be a cool ad to find.
It sounds like something you could probably find online if it's as common as Andy suggests it may
I
be.
just put a link to a video that describes this exact problem.
Oh,
But
good.
Really? You
it seems
found
like
it?
it's always worth a quick search of the obvious solution space for these kind of problems, because yeah, sometimes it's just sitting right there. John, I was going to say, so back to the statics thing. My physics teacher in high school, one of his favorite, he had a problem he called the mirror problem, and this has stuck with me to this day, and it's actually useful. Uh, and the problem was like hanging a mirror or a painting, and you know how you usually have that cable like through the back of something of a painting or something like that you would hang on a wall.
Hmm.
I think he chose a mirror because it's heavy. And the question was actually the way the problem was set up was you have an angle of that little triangle, the cable that's stretched across the back. And if the mirror weighs a certain amount, what is, calculate the tension, but also show what the tension is as a function of the angle,
Hmm.
and basically show, and this is funny because he did this a bunch of times in the class, and he made a big deal out of it. You should know how to do this. You should know how to do this. And then it was a question on the final, and I did not know actually how to do it. But because I didn't really know the difference between like deriving something. He wanted us to show basically the tangent curve. The
Uh-huh.
how the tension goes to infinity when
When the
when the
angle
angle
goes
goes
to
to zero.
zero. Yeah.
And but he was also a super practical guy. Like he took us to the parking lot once because he had a truck, and he wanted to teach us how to tie down a load. And the mirror problem became really important because you could basically like stretch a line across, and then you can attach a line in the middle of it. And I still use this technique today. When you can, so you have like a tight line like over a sofa or something like that, and then you can tie a line through that and tighten it and basically take it from a 0 degree angle to to an actual angle, and put a tremendous amount of tension on it. But also the lesson was like never actually try to make that angle 0, because you will have infinite load. Well, obviously the angle can never be 0, but when you're are aligning your your ropes and stuff, you should, if the goal is to you know to distribute the load, you should choose those angles carefully, basically. Anyways,
Just
so it was a very, what at the time felt to me like I don't know, deriving things on a test. I didn't understand the sort of practical application, but because he took us out to the parking lot to teach us how to tie down loads, like I made that connection
Internalized
later,
it.
and throughout my
Yeah.
career of sailing and stuff, I used that concept like a ton.
Yeah, this comes up in climbing, setting up climbing belays and things as well. But I don't like these problems where they say that this rope is this length and what is the tension in it in circumstances
Yeah.
like this. Because unless the rope
It
length
stretches.
changes, there is no
Yeah.
tension in it. When it's at its natural length, there is no tension. And then the only way you create tension in anything is by stretching it. When you put
Yeah.
a feather on a diamond, the surface of the diamond bows under the weight of the feather. I'm not saying how much, but I'm telling you for sure it bows. And these
We're going
problems
to be talking
that's
about
yeah.
incompressible water here in a moment,
Oh,
I'm
shut
Any
up,
afraid.
shut up.
second,
No,
any
don't do it,
second
don't do
now.
it. But these problems that say this string is incompressible, how does the tension go as you tend towards angles of zero are stupid because it doesn't work like that. The length is not constant. And you can have zero length straps and they work perfectly all right because what happens is that an infinite force starts to apply. The strap stretches an infinitesimal amount. And then now the length is different and the whole geometry of the problem is different and you get a finite force. So the fact that it stretches is really quite important. Young's modulus, Hooke's law, all that kind
This
of stuff.
this is also related. I mean, this kind of thing is also related. If you swing a rock on a string around your head, right? The faster you swing it, the faster you swing it, cycles per second or whatever, the closer that string gets to horizontal. But it can never get too horizontal, and no matter how, right? I mean, you can have it going around 100 times per second, and the difference between that angle when it's going around 100 times per second and going around 1,000,000 times per second is imperceptible. But it is a difference, and it's never gets it to zero. Right, the string has to sag a little bit because it's got to both pull the rock in and support the rock from falling. So it has to angle upward at some level. Nothing like a swinging rock problem to shut down the room. Hey, Sam.
I
Good to
was
see
thinking of
you.
hanging a
Go
piñata.
ahead. Yeah.
Same kind of thing, right? Like how much tension would be required to not let the thing sag at all?
Yeah. And
Or go to infinity.
I was just at a pinata thing. There was an art opening that included a bunch of artistic pinatas that were then beat the crap out of by kids in the audience. And, and it was interesting to me because these were artists putting these pinatas together. And one of the things they really didn't understand about pinata design is that the one thing that's absolutely critical for a piñata is that the top part of the piñata, where it's attached to the rope, can't just fall off the rope. That attachment to the rope has to be really solid so that when people beat on the piñata, the only way anything's coming down is if you break the piñata. You can't just beat it off of its attachment, because there were a lot of piñatas that just ended up on the ground, and then the kids all ran in, beat the hell out of it, and grabbed the candy.
Speaking of brutal teachers, your good friend Professor Felser, and the best professor I've ever had, he designed his test for a 50% pass rate. Like, is that criminal? Like
Well,
literally.
I'll bet he didn't. I never designed my tests for a 50% pass rate, but that's often what I got. I think it is, and I don't mind. I didn't like 50. I didn't often get 50%, but I typically got now. And I'm not sure what you mean by 50% pass rate. I often got averages of 60, 65 out of 100, and I never minded that. I always thought, and I would go over with students why I thought the average should have been 75 or 80, or better. Um, so I was always disappointed with those averages. But I never minded it because you just have to decide what the average
and
means at
and
the
the
end.
and the one
Students are
guy that
often
blows
very
the curve,
disappointed by that.
the one guy
Go
that
ahead.
blows the curve, right? Like it'll be like 51, 52,
Right.
and then one guy will score 98. I had a friend like that.
Yeah. Well, let's see. So let's see. We've got Bert's on stage. He hasn't said anything. Sam, I think, hasn't. If you care to, either
Hi
of you
guys.
guys. Hey, Sam. Good to see you.
Yeah, sorry I'm late. I was in a small business conference all day, so I'm in need of some science to
Well, you must have
wash
been doing
away.
some medical science in there.
No, I was
No,
begging for
just
money.
business.
I was trying to schmooze investors to give me money, but
Oh, you're a schmoozer, huh? To take some schmoozing lessons.
I know.
Okay, well, let's see. So I think we're winding down. Benjamin hasn't had anything to say today, but that's probably not really his cup of tea. This is a little too divorced from quantum entanglement and the kinds of things that he cares about. Bert, I don't know.
A little too static.
Good to see you. Yeah, a little too static, exactly. And Bert's more of an optics kind of a guy. I don't know how much Bert actually worries about ropes and tensions and all that kind of stuff, but
Maybe there was just too much
I know
talk for him
Bert
to get a word in edgeways.
probably a little of that too. So, but anyway, I think I will start winding it down unless anybody does have anything else to say. I'm going to start looking for something to play us out
Hey,
with.
John, after the room, though, I want to have another room, a brief argument about there's always a triangle of forces. I want to defend that position vigorously with
Yeah,
you.
okay. Yeah, no, I'd like to, that would be good. Yeah, let's do that. Let's shut this one down and open an after party. That would be good.
I'll do that. I'll do that in the same house now, shall I?
Okay, great. All right. Well, thanks everybody for coming. I'm not sure what next week will be. I don't think it will be the second in this series yet. Um, but I really have no ideas right now, so we'll see where it goes. And I'll play us out with a little 3-track mind. This is a group that never made it, but should have. And I think this particular piece really needs to be like the credit roll. This is one they should have gotten it picked up by somebody for the music over the credit roll of some movie. It's a wonderful credit roll song called Sacred Fire.